Okay.
This is lecture 21B, special lecture of math problem solving, Math331 on tour. We are in Swarthmore today, and I will turn it over to the first presenter.
Okay, I'm John. I'm a sophomore here, and this is a really interesting problem, so I just want to present it. So I'm just going to say a little bit about what it means. So it's 2013 A5. The problem is it's a geometry problem. So the idea is, I'm just going to read it first. So for m larger than or equal to 3, a list of m choose 3 real numbers a, I, j, k is said to be area definite for Rn if the inequality. So if this inequality holds for every choice of n points a1 to am in Rn. So what this actually means is we can do an example here. Let's see, what's the example given in it? So for example, we know A123 equals A sub 124, 134 equals 1, and A234 equals -1 is area definite in R2. The reason for that is if you pick any 4 points, A1, A2, A3, A4, and you connect them. So if we do write down the inequality here, what we'll have is A1, 2, 3, and then area A2, A3 plus A1, 2, 4. Let's just do, what can we do here? Let's just do, like, for example, A1, A2, A3, just to make the notation a little bit cleaner. A1, A2, A4 plus A134, A1, A3, A4. This is getting a little dangerous here. Everyone can see it? Probably. Okay. Minus plus A234, A2, A3, A4. I think you can check this should be 0. No, wait, this is not 0. As it turns out, this should be, so if we look at this, A123 is 1, A124 is also 1, A134 is 1, and A234 is -1. So what we really have here is A123 plus A1, A2, A4 plus A1, A3, A4. So we have the only overlap, I believe, is right. So this should be A1, A2, A3 plus, sorry. So these two should equal A1, A2, A3, A4. So the area of the whole thing. And then plus this minus this. So this minus this is actually exactly A1, A2, A3, A4, A1, A2, A3. So
you cover the top twice, but then you lose one.
Exactly.
A2,
Right. So this is larger than or equal to 0. So this is why this list of numbers is area definite for R2. Okay. So we can do the same thing for every other dimension as well. So what the problem asks is, if a list of number is area definite for R2, it's also area definite for R3. We certainly know it's true the opposite direction, right? If it's area definite for R3, then it's area definite for R2, because we can just choose the endpoints to be on the same plane. So how do we do this? Like, if we know this is area definite for R2, how can we translate that into R3? Do you guys have any idea, maybe? Like, let's say, for example, we have endpoints in R3. We just know that this list of numbers is area definite for R2. Like, is there any way, anything we can do, any kind of operation we can do that somehow we can move points in the 3 dimension to maybe 2 dimension and make use of this inequality here in R2.
So do you want to take a projection? Or?
Taking a projection. Right, so that would be a good idea, right? If let's say we have all of the points in this classroom, we can just take the projection on this blackboard, and then what we really, actually, when we say A1, A2, A3, where they actually are, it could be all the way over there, right? Like it could be anywhere, but like we're just taking a projection here, so we can make use of the inequality, right? That seems like the only way we can make use of the result, that this list of numbers is area definite in R2, in order to show anything about whether it's area definite in R3. So I think this probably just boils down to how do we do the projection, right? Is there any way we can choose some plans in R3 where after we do the projection and maybe add them all together, it will somehow magically give us the original inequality, right? So I think that's the main challenge here.
And are you doing this with just one projection?
Well, one projection is definitely not enough, I feel like. If one projection works, right, what you need is you need to find a plan in R3 that somehow, after you do the projection, like all the areas of the triangle, at least in terms of proportion, will be maintained, right? Like, so if the triangle A1, A2, A3 is twice as large as triangle A2, A3, A4, if one projection is enough, we want it to be, after we do a projection, we want it to be as well, like twice as large as the other triangle. So I don't think that's possible, right? It does seem unlikely that's going to be the case. So how do we do this? Let's just start with the 4 points, right? Because I think it will be a little bit easier to do that. With the 4 points, the easiest configuration we can think of is maybe we have 3 of the points on the same plane and maybe a point somewhere here, right? What's it called? Tetrahedron? Right. So we have a tetrahedron, right? Let's say this is the case. Let's say we have a tetrahedron. How do we do this? I mean, one way we can do this, we can take the projection on each of the face of tetrahedron, right? So actually,
so there's 4 choose 3 planes that you would get.
right, so that will give us 4 choose 3 planes.
And so would you do something for each of those planes and then combine?
Right, so I mean that's one thought, right? That's one idea to do that. As it turns out, I don't think that works because, well, actually, let's just derive a little bit of result that might be useful, right? So let's say if we have a plane here, we have a triangle somewhere in R3, and then we do the projection. And this, of course, also lives on a plane somewhere because every 3 points define a plane in R3. So what is the area of this? Let's suppose this is A, and let's suppose the angle between these 2 planes is theta. I think it can be shown that A prime is just cosine theta times A. Take the absolute value, I believe. Does this seem obvious? Or okay. The reason for that, I don't remember why that's the case. I'm pretty sure that's true, but I don't remember why. Actually, why is this the case? Let's just pretend this is true for now. We can move back to here later. Why is this? Okay, so we know after we take the projection, the area of each triangle is distorted by this coefficient, right? So if we just take the tetrahedron and take each face, you'll have the coefficients when they add together with each face, you'll get a different coefficient. So you will still distort the area a little bit. So the idea here is so I tried everything with finite number of planes. As it turns out, you just can't do it with finite number of planes. So I just said, well, let's just do infinite number of plans. Let's just do every single possible plan in R3. Let's do a projection. Because it's equal for every triangle, right? Like for each triangle, the amount of distortion for each plan, if you rotate the plan in every direction you have, the overall distortion for each triangle is going to be the same. So now you'll have this inequality. So that's the basic idea.
But if you have infinitely many planes, you have to start worrying about convergence of
Right.
combinations. So are you gonna put in weights, or?
Well, I mean, so the way I did it is, let's suppose O is the origin. And also for each plan, we can assign a normal vector n, right? So what I wrote earlier can actually also be written as this: aj, ak equals cosine nijk n times the area of aijk. So if we look at all the plans that pass through, let's say, just any point in R3, let's call it O, right? The origin. And then what we really want to do is let's just rotate the normal vector in all directions, right? So you have a sphere, a unit sphere centered at O. And then with each normal vector, you'll define the plan. And for each n, you'll get inequality based on R2 after projection.
So you're then going to integrate over all choices of the normal?
Right. So that's the idea. So let's say on this sphere, right? You have this point A. Let's define the function f of A as just 1 smaller than I, j, k smaller than or equal to m, cosine OA, nijk, aijk, and area aijk larger than or equal to 0. So because the list of numbers is irredefinite in R2, we know this holds for every choice of A on this sphere. So next thing we do is let's just do this, right? S. And S is the sphere. And then we just do f ds. We know this is larger than or equal to 0. On the other hand, if we actually add all of these terms together, right? So we have what we really have here is a list of an infinite list of inequalities. If we add all of them together, as it turns out, this number, because it's symmetric, like wherever nijk is, if you rotate it on the sphere, eventually this added together, it's going to be constant.
You get the same thing for every choice.
Exactly. We have the same thing for every choice. So we know this number, right, OA, nijk, it's just going to be constant. Let's call it C, right? So we just divide this by C, and we should get this inequality, which is why this list of numbers should be irredefinite in R3 as well. So this is just a sketch of the proof. From here to here, it takes a little bit of work, I think. But it seems intuitive enough, I think.
Now, could you push this up to now R4?
I don't know. I'm pretty sure it can be done. I don't think there's any reason why it will work from R2 to R3, but not to R4. I think the idea is the same. You just need to do the projection into R3 for every single possible R3 space center at O. Yeah, I think it's probably true. Yeah. Do you guys have any questions?
What's OA again?
OA is just so basically any unit vector.
That's pointing in this.
So you can just move it on the sphere anywhere, right?
Oh,
like
okay,
A is on
so
S
it's just
really.
The arbitrary, the fourth point.
What?
The fourth point in the space. So you project A to that plane.
Well, what I'm really doing here is I'm trying to assign A can be anything on the sphere, right? Right. So yeah.
Okay.
And this sphere is just a unit sphere centered around an arbitrary point O. Like it doesn't really matter where the O is, right? Because from here we know the amount of distortion on each turn of the inequality only depends on cosine of the angle between these normal vectors. So we know if we move it around because of symmetry of the space, like there should be a constant here. So we just divide it by this constant.
But wait a second, but there's certain triangles that's already on the plane.
Right.
Where
So
the factor is now C. So the C is only for.
But if you're on the
Real.
it's going to be measure 0.
well, if it's on the plane itself, there's no distortion, right?
Yeah, no.
Right. There's no distortion. But if it's vertical to that triangle, you're just going to get 0. So this is taking into account all of those effects, right? Because now A can move on the sphere wherever it can be.
Oh, okay.
So it's moving around
I see.
to make sure it's equal for everyone, right? Okay. Any more questions?
Very nice.
Okay, great.
So it's a nice example of combining cases of looking at lower dimensions. How do you push the information up?
Right.
You want to start erasing this as he gets ready? So you just push
Friendly. Maybe I'll just hold it.
do you want me to flip you?
Sure.
Can you button up the top button? That'll be easier. Then you can just put between these two.
Clever.
Now you guys know why I dressed the way I do for class.
It's helpful.
Oh, it is.
Convenient. Okay. So I'm going to be talking about a project order problem, specifically number 14, which is about Collat sequences. Also, my name is Devin. So the Collat's conjecture basically states we have this function on natural numbers, and we define it as if the number is even, we divide it by 2. And if the number is odd, we multiply it by 3 and add 1. So, this makes sense. If it's even, we can divide by 2. If it's odd, then we're going to multiply by 3, add 1, then we'll get an even number, and we'll divide by 2, and it's going to do some crazy thing. And the Collat's conjecture states that no matter where you start, you're going to get down to 1 eventually. And then once you get to 1, you're going to get to 4, and then 2, and 1, and then you're in a loop. And that's, as far as I know, still unproven. But this question asks for something a little bit simpler. It says, define the length of a number, I guess call it L of n, to be the number of steps it takes iterating f of n to get to 1. Let's write it this way. Equals k such that when you iterate fk times starting from n, you get 1.
And that's the first K. The smallest K.
Yes. And so the question is basically just you start at some point and flip around a little. And certainly we know for small values, we've just verified with computers, that we're always going to end up at 1. And so the question asks you to determine what's the largest value of n, or L, for n in, I think, 0 to 1,000. Well, maybe greater than 0. And the trick to solving this is basically to note that, well, I guess I sort of wrote it suggestively already. It's to note that once you get to a certain number, if you've already figured out what L of that number is, then you're done, because starting from a given number, you're only going to have one sequence iterating here. So if I happen to know that L of 13 is equal to, I don't know, 10, I think it's something around there. If I happen to know that, then when I look at L of, say, 26, well, I start at 26, I apply f, I get 26 over 2 is 13. But then I know how long it takes me to get from 13 down to 1. It's 10. So L of 26 is just going to be L of 13 plus 1, which in this case would be 11. Again, I'm not entirely sure if that's accurate, but it's pretty close. So the way that we can solve this problem is essentially keep track of all the values of L that we compute. And so specifically, we can write a function that computes L. And what it will look like is computes L. And essentially what it will look like is we'll keep some array of computed values. And every time we find a solution for this, we'll store it in the array. So what we can do is, if we've already computed, well, L of 1 is 1. If we're at L of 2, then the first thing we'll do is check if n is in our array. It doesn't really matter. It needs to be some sort of dictionary type where you put in an n and get out the corresponding thing that you put in there earlier. Yeah, an array of tuples would be sufficient. So check if n is in our storage. If it is, that means we already computed this once. We know the answer. We can just return that. I should not have given this such a long name. Good coding practices are not as good. Thank you. It's good practice if I were actually typing this. So return whatever we stored in there. So if you've already seen it, return it. Otherwise, we don't know the value here, so apply our function here. Let me see. Val, there, I'll have it be short. Val is going to be equal to f of n, or sorry.
Maybe n time is the next step?
Yeah, so what we're going to do is we're going to say, okay, well, it's equal to however many steps f of n takes plus 1. So it's going to be, we're going to recurse on compute of f of n, where f is that function defined over there. Yeah, still on there. Plus 1, because we iterated f one time plus the number of times it takes to get from f of n to 1. And then, before we return, we just say that computed values of n is equal to val. Because now we've already computed this, we don't need to compute it again. So we can store it here, and if we ever ask for the value of this particular number, we'll catch it in this check and return it. And so
if you have a number that takes 5 iterations before you return to something you know, you would then store 5 new values.
correct. You would store the value of f of n, the value of f of n, et cetera, until you get to something you know where this happens. And then you just return what you found. And so what we can do is we can just start at 1 and write a loop that repeatedly calls compute L on 1, 2, 3, 4, 5, all the way up to 1,000 with this technique, which is called dynamic programming. Oh, my. Hello. With this technique, which is called dynamic programming, it will be polynomial time. It'll go pretty quickly. The numbers that you go through are going to go way above 1,000. You're going to get really, really, really big numbers. And fortunately, my compiler handled them naturally, and I didn't have any problems with that. But it is possible you would have to write special code for dealing with them or go import a big num library. But otherwise, you're fine. So you just compute this for each of the n's from 1 to 1,000, and then go through the array, find the maximum, and return that.
And the way you're programming, you only need to assign memory as you find computed values. So you're not making a huge list.
Correct.
You said some of these numbers get very large.
Mm-hmm.
So you are not setting aside a certain memory block at the start of the program.
Right. So you would use some nice, smart data structure that adds as needed.
Yes. Excellent.
Right.
And then
I also have a question. Do you know if there's any connection with other, like what is this theorem used for? Is there any insight we get from this?
Which theorem?
This theorem you are.
Oh, about the 3x plus 1?
Yeah.
Or
It turns out the 3x plus 1 problem itself is connected to a lot of really good mathematics. And I'll try to put some good links. Jeff Legarius has written a lot of wonderful papers on this. Probably my favorite quote about this problem is, this was described as a Soviet conspiracy to slow down American mathematics. Because every time Kakutani described this problem, people said, oh, no, this isn't that bad. And they'd start working on it for a month and then give up in frustration. But it would slow down their productivity on other things. Urdush has said mathematics is not yet ready for problems like this. But a lot of it is, it's a deterministic system that behaves very randomly. So you give me a starting seed, it's predetermined what's going to happen as you iterate. But in terms of are you dividing by 2, are you multiplying by 3 and adding 1, these seem to behave very randomly. And you can model this as a random process. And it turns out you can predict things such as what is the length of time you would expect to take before a given number collapses down to 1. And you get some kind of Gaussian behavior for that. And what's the longest amount of time it takes? This is like log law that goes on there as well. So there's a lot of great mathematics, and this can be used to model a lot of random systems. What you'll often do is you'll have the maps will be either dividing by 2 or multiplying by 3. If your number is really large, you just drop the +1, and it makes it a lot cleaner. It's no longer exactly what you're doing here, but now you'll say, maybe I'll multiply by 3 with probability half, and I'll divide by 2 with probability half. Or something more involved. Some variants of this problem, they do it all in one step. You multiply by 3, add 1, and pull out as many powers of 2 as you can in one step.
Yeah. That's a very reasonable thing to do.
Excellent.
Actually, I still don't have one.
Okay, if you don't want to, that's fine.
I'll just
so I will
refrain from
that's fine. So I will do the triangle game, and then you're on for the triangle game. Okay. So I think we first started talking about the triangle game on one of the many days when my daughter was visiting my class. I think we went through a 5-week period where there were 6 days both of my kids made it to school. Now part of this was we did have 1 week of school vacation, but we also had a huge number of snow days and a huge number of sick days. Okay, so does everybody remember the triangle problem? So you start off with the triangle, and you can partition it any way you want. I'll partition it maybe in a nice way like this. And well, I'll do one more level. I'll put a big 0 here, a big 1 here, and a big 2 here. You can only use 0. Yes?
One way to remember the game was that you put money on the table that your
So,
daughter was going to win. So.
No, it was my student would win, so here.
Oh, yeah. That that your daughter was going to win
Right.
the game, so the student will
So
not win.
I'll put down 20 Canadian. In Williams, it's actually not that bad to have Canadian money because we are not too far away from the border. So if anybody can beat me in the triangle game, I will give $20.
But this is unfair to software students.
It doesn't have as much value to us.
Fine. I'll do 25 Canadian. Now it has more value.
No, but still, like, they don't have more incentives for the game.
Fine.
I'll even put my credit card.
No, because this is recording. I don't want my credit card anywhere near that value. I'll add 20 American.
Okay.
All right, if you beat me. All right, and here's how the game is played. On this side, you can only put down 0s and 1s at all the vertices. So we have 3 labels we have to do. On this side, you can only do 1s and 2s. And on this side, you can only do 0s and 2s. And on the interior, you can do anything you want. And the way we initially played it is you would get the most money if we alternated moves. If you do 2 moves to every move I do, I'm going to take back, $5 Canadian. If you do 3 moves for every move I do, I'm going to take back 20 Canadian. And if you do 4 moves, I could take, I split the 20 to 10s. And so depending on how many moves you want to do, I will put less of my money at risk. So if you're trying to win, your job is to prevent a triangle from labeled 0, 1, 2. You want no 0, 1, 2 labeled triangle. My job is to stop you from getting a 0, 1, 2 labeled triangle. So if you wanted to create one, if you got to do 2 moves, not so bad. 1, 2, I win, right? So that's why, since you have the possibility of doing multiple moves, you have to prevent the existence of a 0, 1, 2 triangle. So let's give me some labels. What do you want to put down here? 0. 1. Okay, so now I've got a 0, 1. So if I got to move, I'd put a 2 here. So I'll let you move. What would you like to put there? 1. Okay. I've got a 0, 1, so I'd love to put a 2 here. I'll be nice. I'll let you go again. What do you want to put here? It's got to be either a 1 or a 0. I'm sorry? Let's put a 0. All right. So now I've got a 0, 0. I've got some freedom over here. Maybe we'll hold off. I've got a 0, 1. What do you want to put here? We can always go back and change some of the moves. So what would you like to put over here? It's either a 1 or a 0. 0? All right. Now what do you want to put over here? It's got to either be a 1 or a 2. 2. Okay. I can't put a 0 here now, but I couldn't have put a 0 there anyway, so that's not a problem. 1 or a 2.
You cannot put a 2. You don't want to put a 2 because you lose. You also can't put a 1.
Oh, if I put a 2 there, I lose because I've got a 0 and a 1. Okay, so I've got to put a 1 here now. Now that's making things easier. I've got a 0, 1. I don't want to put a 2 there, so I've got to put a 1 here. I've got 0, 1. I don't want to put a 2 here. Well, actually, I do, but you don't. So you can't put a 2 there, so you've got to put a 0. We've got 0, 0. We've got a lot of freedom. So,
Zero triangles.
do you want to put?
We have already.
Yeah, I was going to say there's already a 0, 1, 2 triangle that people haven't
Very
noticed.
top one.
It's the very top one is the 0, 1, 2.
Okay. But you can get that 0 on the left and maybe put a 2.
So,
Yeah, you also have 0, 1, 2.
right. So, I've already got the 0, 1, 2 triangle here. So if I put a 2 here, I can then change this maybe to a 1. Right? And I'm still okay now. So now I've got a 2, a 1. I can't put a 0 here, so I've got to put a 2 here. And now I've got a 0, 1, 2 triangle over there. And so now, let's say I put a 2 over here. So you almost did it. Only one triangle, I think, came into play. So the first question is, who cares about this game? So it turns out this is called Sperner's lemma. There always is at least one 0, 1, 2 triangle. And this is the key ingredient in one of the proofs of Brouwer's fixed point theorem, which is one of the key ingredients in Nash's analysis of game theory and led to Nash equilibrium. And it led to a Nobel Prize. Admittedly, only in economics, but it's... Actually, it's not clear. I don't know if it's still called a Nobel Prize in economics because economics was not one of the original categories and was added later. So the question is, how would you prove something like that? No matter how you label, there is always going to be at least one triangle. So what should be your first thought in looking at a problem like this? And I know we talked about this months ago. I'm sorry? Nope, that should not be your first thought.
My first thought is induction.
Induction on what?
Number of triangles or something along that, how it's subdivided.
So you can make an argument by induction, but not an induction on the number of triangles.
The number of moves.
Not the number of moves.
Not the shape.
Not the shape. So it's a hidden parameter. So this is very similar to the integration problem we did in the last or 2 classes ago. We were integrating from 0 to 1 of x to the 5th minus 1 over log of x dx. And the key thing was to replace that 5 with a t. And that gives ourselves a free parameter. And don't look at this one specific problem. This is a realization of a more general phenomena. So here I'm looking at points on a triangle in a plane. What might be easier to look at?
Points on a line.
Points on a line. This is almost a 2-dimensional game. Is there a 1-dimensional game that we should analyze? And after we analyze the 1-dimensional game and the 2-dimensional game, we would have a tetrahedral game with labels 0, 1, 2, 3.
I'm just wondering, is the thought here to make a smaller, still kind of big triangle with 0, 1, 2 at the bottom, and then you reduce it to a smaller k?
So a lot of it depends on how you partition. Can you show that something keeps surviving? So let's look at the lower dimensions. So is it this way? Okay. So let's look at lower dimension. So there's a lot of ways to do this. For the lower dimension here, I think the easiest is to almost do like a monovariant. How many 0, 1 triangles do we have? Okay, now they're called segments. So how many 0, 1 segments do we have? 1. Let's add a point. If I label this point 0 or 1, do I change the number of 0, 1 segments? No. Let's add another point. If I put a 1 here, do I change the number of 0, 1 segments? If I put a 0, do I change the number of 0, 1 segments? No. So either adding a 0 or 1 doesn't change anything. Let's put a point over here. If I label it 0, do I change the number of 0, 1 segments? If I label it 1, do I change the number of 0? By how much? By 2. And so what we see is every time we add a new point with a label, we change the number of 0, 1 segments by an even number, by either 0 or by 2. So if we start off with 1, 0, 1 segment, then we know since we're only changing it by even numbers, we have to end. So basically, you have 0, 0, and you put in a 1. This is a +2. You could have a 1, 1, and you put in a 0, and that's +2. And all else is no change. So this is a monovariant. Start odd, end odd. Now this may seem silly, but the odd numbers have a fascinating property. The smallest odd number is positive. We don't consider negative numbers. A lot of these things, we're counting objects. When you're counting objects, you're not going to have -2 or -3 objects. The smallest you count could be a 0. If your count is odd, it must exist. There must be a realization. So this is one of our most useful proof techniques. You prove a quantity is odd, therefore it must exist. There must be a realization. I also like starting in a lower dimension and building up. So we understand what's going on in one dimension on the line. Now we want to build it up to a triangle. And then once we build it up on a triangle, we should probably be able to expand up to a tetrahedron. And this is related, so I'm really glad we got the geometry question to start the day. We show that you can move up from, if you know this on planes, you can push it up to 3 space. Then the natural question is, can you push it from 3 space higher? As we were hearing about that geometry problem, I was wondering, can you go the other way? Can you go from, you know it for lines, do you know it for planes? Well, given that you want 3 points to get an area, you're not going to have 3 points on a line. Okay, so we're all comfortable with the lines. And now we're trying to do the 2-dimensional case. So I'm going to go through the proof in the 2-dimensional case, and then I am going to show a little bit of how this connects to Brouwer's fixed point theorem, and why this leads to good mathematics. Okay, so the most difficult thing when you're doing combinatorics is to figure out what should you count. You want to find something that's related to the problem and tractable and easy. So we have some knowledge. We know the number of 0, 1 segments on this lower boundary is odd. Number 0, 1 segments on bottom is odd. The idea is we want to somehow get the number of 0, 1, 2 triangles is odd. Because if there's an odd number of 0, 1, 2 triangles, then there must be a 0, 1, 2 triangle. So what's the relation? What does a 0, 1, 2 triangle have that's related to something we have on the bottom? It has a 0, 1 edge. Let's count 0, 1 edges. So the goal is to count 0, 1 edges on our triangles. And the reason this is a natural thing to count is it allows us to use the lower dimensional case. And the 0, 1, 2 triangle, so let's let T 0, 1, 2 be the number of 0, 1, 2 triangles, is the number of 0, 1, 2 triangles. And it contributes 1, 0, 1 segment. What about the T 0, 1, 1 triangles? How many segments does that contribute? Contributes 2 segments. What about the T 0, 0, 1? How many does that contribute? What about the other triangles? Yeah, they contribute 0, so let's not bother with them. So if I want to count the number of 0, 1 segments, so the number of 0, 1 segments, I can take all the 0, 1, 2 triangles. Every time I have a 0, 1, 1 triangle, I get 2 segments. And every time I have a 0, 0, 1, I get 2 segments. So does this formula count the number of 0? Okay, I see head shaking. What's wrong with this formula?
You are potentially overcounting edges if they're part of more than one triangle.
Right, so if an interior edge, a 0, 1 edge, is going to be counted by 2 triangles. In fact, every interior edge is counted by 2 triangles. I'm sorry? Right. So the interior edges are double counted, and then, as was just remarked, the boundary edges are only counted once. So the simplest way to fix this formula is, well, let's just double count all the boundary edges and then divide by 2. So now what we can do is we can add the number of 0, 1 segments on the bottom. And this will be twice the number of 0, 1 segments, because we've now double counted. Everything that was interior was already double counted because it's in exactly 2 triangles. Everything that was on the boundary, the only boundary that works is the 0, 1 boundary. So if we look at things mod 2, we have even equals t 0, 1, 2 plus even plus odd. This is not a hard equation to solve. The only solution is this must be an odd number. And therefore, there must be a 0, 1, 2 triangle. And the number of 0, 1, 2 triangles is odd. So there could be multiple ones, but there's at least one. And now what you could do is, if you want to do 0, 1, 2, 3, 4, you would put a vertex coming out. And you would start off with, we know that the number of 0, 1, 2 triangles in the plane down here is odd. And this just becomes a game of notation. So this is called Sperner's lemma. So I have 2 young children, and so for me the way I get math into them is I turn things into games. My kids have learned that if Daddy wants to play a math game that he's created, don't do what he wants. But of course, then that gives me an incentive. Well, I'll then take the bad strategy because they'll want to switch. But they're always very skeptical now about, whenever somebody offers you a game, there's often a reason as to why they're doing things the way they do. We saw a problem on 3x plus 1 earlier today, the Collatz conjecture. One of my earliest papers was proving that if you look at the distribution of leading digits in iterates of the 3x plus 1 map, they actually satisfy Benford's law. About 30% of the time, the first digit will be 1, all the way down to about 4.5% of the time, the first digit will be a 9. One of the great applications of this is the IRS uses this to detect tax fraud. And in fact, I was contacted by members of the IRS, but I will not talk about that while the camera is rolling. So it's amazing how you see the mathematics in very different places. People actually use Benford's law as a gambling thing. So if you have lots of data sets satisfy this digit bias of having a huge tendency to having lower digits. And I think it's around 70% of the time, your first digit will be 1, 2, 3, or 4. So if we say, here, let's play a little game. We'll open up the book at random and we'll just point our finger down. If it's a 1 to 4, I win. If it's a 6, 7, 8, 9, you win. All right, I'll give you 5. You're getting 5 numbers to my 4. And just a great way to take advantage of people's inexperience on the mathematics. All right, so the question is, why would we care about something like Sperner's lemma? So a lot of it is Brouwer's fixed point theorem. So I don't know, have you guys done any fixed point theorems? So a fixed point theorem is trying to solve f of x equals x. So we want to solve f of x equals x. It turns out almost all of mathematics can boil down to finding a fixed point. Let's say, for the sake of argument, you don't want to find f of x equals x. You instead want to be difficult, and you want f of x equals a. So I want to find a new function, g, where g of x equals x is the same as f of x equals a. So if we look at f of x minus x plus a, and you want this to equal, I think it should be plus x minus a. So imagine this equals x. Then that's the same as f of x equals a. So if we call this our function g of x, finding a fixed point of this is the same as solving f of x equals a. So you can convert a lot of these problems to fixed point problems. There's lots of different kinds of functions you can look at where you can prove a fixed point exists. So if f is a contraction map, it turns out it's going to have a fixed point. And there's a technical definition of what it means to be a contraction map. I'm not going to go into that right now. One of the great applications of this is solving differential equations, is proving that if I give you a differential equation, there is some interval of time in which case the solution will exist. And you can often solve this using fixed point theorems, and I'll post some stuff, and if people are interested, happy to do some lectures on this as to why we care about stuff like Sperner's lemma. Another way of talking about some of these fixed point theorems, they sometimes phrase this as the coffee theorem. Imagine you have a cup of coffee, and if you're going to be a mathematician, you have to learn about coffee. And you stir up the coffee, and then eventually it stops. And we will assume that this is the idealized glass of coffee. So the coffee is completely continuous. So the coffee theorem says if you stir it continuously, at least one point of coffee must return to where it started. So when I talk about a fixed point theorem, I have to give you a region of space, and I have to give you a map. Not all regions of space, when I have mapped from the space to itself, will have a fixed point. Can anybody think of an example of a space where I can come up with a map where there is no fixed point for that function? It's a nice continuous map.
You rotate the complex number without zero?
Yeah. Or rotate a donut, rotate a circle. So if I give you a circle like this, and my space is just the boundary, and I say, f of x is just, well, I'll do it as f of e to the I theta is e to the I theta plus alpha, where alpha is strictly between 0 and 2 pi. I'm just rotating the whole circle by alpha, and there will be no fixed point. But if I then filled in the whole space, so it's not just the boundary, but it's the whole region, then the origin would be a fixed point. So your space should have certain nice properties if you expect there to be a fixed point theorem lurking in the background. So probably we don't want any holes. Because if there's a hole, well, maybe we can just rotate about the hole. So you would probably want your space to be simply connected. I don't know if you've heard terms like this. So this is where real analysis becomes very useful, or topology becomes useful. So I want maybe a nice simply connected space. Maybe I want my space to be compact, so I want everything to be finite in some kind of big circle of radius r. Well, this is kind of easy to put inside a circle since it's a circle. Maybe I want my function to be continuous, but not necessarily differentiable. And so it turns out that you can use Sperner's lemma to prove the existence of a fixed point. And the way it works is the following. So let's just do things in 2 dimensions. I want a basis in 2 dimensions. How many elements should my basis have? 2. But there's nothing that says I have to use the most efficient basis. What I'm going to do is I'm going to do a basis with 3 vectors. v0, v1, and v2. And I'm going to write any vector as a linear combination of v0, v1, and v2. So it'll be t0, v0, plus t1, v1, plus t2, v2. The ti's are between 0 and 1, and t1 plus p2 plus t3 equals 1. So I'm not going to go through the calculations right now that actually will sweep out the triangle. So these are called barycentric coordinates.
So
Yes?
what exactly is the relation between the vectors and the triangle?
So there are three vectors. The way I've drawn it, maybe think of V0 as the origin.
Okay.
And then if I take this linear combination, that's going to give me a point in the plane.
So like, it would be reasonable to say like V1 is the 0 to the 1 vector, and V2 is the point 0 to the point 2.
Exactly.
And V0 is 0.
Exactly.
Cool.
Right. And then if you look at this, this looks like a three-dimensional space because I have three numbers, T0, T1, T2. But since their sum is 1, it's really a two-dimensional space because once I give you T0 and T1, then T2 is determined. And this is where you can have the fun of, we're really going to start counting with 0, not 1. Unfortunately, yes. A lot of the stuff, they like to start counting with 0 because we really only have two free dimensions. And so they want to count T0, T1, T2 to emphasize the fact that it's two free dimensions, even though we're writing three vectors. So you see the two floating around and not the three. So it turns out any point in the inside triangle can be written uniquely. If I'm going to be a point on the boundary, how much T2 do I have? 0. If I'm going to be on this side, how much T1 do I have? 0. Okay, so you can begin to see what's going on. So what I want to do is I want to prove a map from the triangle to the triangle has a fixed point. And then if I can prove a map from the triangle to the triangle has a fixed point, then this is where you start doing some results from topology and say, well, maybe I can take my region and I can map my region to a triangle, show it has a fixed point in the triangle, and then map back, and the fixed point on the triangle will map to a fixed point in the original set. I'm not going to bother doing stuff like that. I'm going to just work on the triangle for today. But the principle is the same. Okay? So what I want to do is I want to show, F is continuous. F maps the triangle to the triangle. Claim F has a fixed point. What do you think will be useful in proving the existence of a fixed point? Sperner's lemma, right? There's probably a reason I started today with a triangle game and talking about Sperner's lemma. So what we want to do is for each F, we want to associate things in such a way that Sperner's lemma is going to come to the rescue. Now what's nice about Sperner's lemma is it says no matter what triangulation you have, as long as you label it in this legal way, there will always be a 0, 1, 2 triangle. So what we could then do is we could then do a refinement. We could take each triangle and cut it and subdivide it in half. And just keep playing this game. So for each triangle we replace with 4 triangles and keep doing a finer and finer and finer mesh. And if we do that, we're going to then have a sequence of 0, 1, 2 triangles. Do we know that each triangle has to be inside the previous? Nope, they can be hopping all over the place. But this is a compact set. And this is where we like to use some results from real analysis. I have a compact set. I have a sequence of triangles. There's got to be a subsequence that converges. Has everybody seen enough analysis to be comfortable that if I have a sequence of triangles? You can say no if you haven't. All right, so let's do a brief aside. So this is called Bolzano-Weierstrass. And so if I have a compact set, given any sequence, it has a subsequence that converges. Any sequence in a compact set has a subsequence that converges. And so what we can do is for our triangles, we can always look at the sequence of the location of the vertex labeled 0. That's going to form something that will converge. So here's the simple proof. Typically we do it on the interval 0, 1. Imagine we have infinitely many points. Divide the interval in a half. Then either the first half or the second half has to have infinitely many points. Let's assume it's the first half. So choose any point in the first half and call that A1. Divide this in half, and now we have 2 intervals. Since there were infinitely many in the first half, one of these 2 must have infinitely many. Let's say this time it's the second one. Choose any point in that, call that A2. Divide this in half, and keep going like that. And then what you'll see is the mesh is getting smaller and smaller and smaller. And then in a real analysis, this is not enough. You have to do a little bit more work to say it converges. Is this hand wavy enough for today? I have a friend who left mathematics when he got as a contradiction the integer was equal to 1/2, and the professor said, but you haven't shown 1/2 is not an integer. That's the day he became an engineer. So this is acceptable that you agree that the mesh is getting shorter and shorter and shorter. Sure. So now, first I had infinitely many points in an interval of length 1, then infinitely many points in an interval of length 1/2, then infinitely many in length 1/4, then infinitely many in something of length 1/8. So the mesh at each stage is getting smaller and smaller and smaller. So if you want, you can look at the left endpoints are always increasing, the right endpoints are always decreasing, and the distance between them is going to 0. So the left and the right endpoints have to converge to a common value, and by the sandwich theorem or the squeeze theorem, your number has to be squeezed in. So that does what's going on in the plane. If I do it in the triangle, it's the exact same thing. One of these 4 triangles has to contain infinitely many. Let's say it was the top one. Then I subdivide this into 4 triangles. Let's say it's this one. Then I subdivide this. So this is the power of the Bolzano-Weierstrass. So what we're able to do is if we go back to our original triangle, it's tracking well today. So I know that there's a 0, 1, 2 triangle. Then I subdivide, there's got to be another 0, 1, 2 triangle. Then I subdivide, and there's another 0, 1, 2 triangle. And I keep sub, and I get a sequence of triangles. And their girth is getting smaller and smaller and smaller by a factor of 2 each time. And if I look at just the 0 endpoints, I'm going to get a sequence that converges. And if I then also look at the right end, the 1 endpoints and the 2 endpoints, that also converges, and it's going to converge to a common point. So I'll have a sequence of triangles that converges to some interior point. Or maybe it converges to a point on the boundary. It converges somewhere. Okay, so we're trying to show that a continuous function has a fixed point. And the idea is to use Sperner's lemma. So what we want to do is we want to have a sequence of triangles that encodes something about our function. So what I want to do is the following. If f has a fixed point, does f have a fixed point? Yes. So without loss of generality, f has no fixed point. It suffices to consider this case because the case where f has a fixed point, it's not hard to show f has a fixed point. So what we're going to do is to each point in the triangle, we're going to associate a label. It will be the smallest index where f of the point does not have the same value as the point. So let's say I have some point P in the triangle. I can write P as T0, V0, well, let's call it TP. TP, V0 plus T, TP0 plus TP1, V1 plus TP2, V2. And then I have f of P, which I can write as T f of P0, V0 plus T f of P1, V1 plus T f of P2, V2. What do we know about these 2 points? They're not equal. Because if they were equal, f would have a fixed point. So if they're not equal, there must be a first index where they differ. And so what we'll do is we will find, there's so many different words we could do. We could do we could do L for label. We'll do the label function of P is the smallest index such that the new point has a lower t value there. T value at that index. So let's think about this point V0. So if we're at the point V0, this is the coordinate 1, 0, 0. We're 100% in the v0 direction. Because we're not a fixed point, I have to move off from here. So what's the first coordinate where my index has gone down? Has to be the 0th one. And that's why I'm going to label this 0. If I look at this line over here, along this line, I only have t0 and t1. I don't have any t2. Is it possible that both t0 and t1 increase? So could both t0 and t1 increase along the bottom line? No, why not? Yeah, t2 would be negative. t0 plus t1 already adds up to 1 along this line. If both of them increased, or even one increased and one stayed the same, then that would exceed 1. So I know along this line, the first index that goes down is either t0 or t1. Without loss of generality, by symmetry, whatever words you want to say, the same argument applies on the other sides. So what this tells us is that we label the bottom with 0s and 1s. We label this with 1s and 2s. We label this with 0s and 2s. We're in the setting of Sperner's lemma. Is it possible that all the indices don't go down? Well, since the sum of the indices has to be 1, if they all stay the same, it's a fixed point, and we're assuming there's no fixed point. If they all go up, the sum is greater than 1. That can't happen. So we know that this function L is well defined. So you always want to make sure your functions are well defined. So L is well defined. Given a point, there is a unique label. And so because of that, given any triangulation, we can now label, and now we are assured that there's a 0, 1, 2 triangle. So now we have a sequence of 0, 1, 2 triangles. And now all that we have to do is figure out what goes on in the limit. This is where I'm watching the clock a little bit. We still have plenty of time. Even with traffic, I can't believe American Airlines will leave on time, and I'm quite happy if this is recorded. So we have a sequence of triangles. And on these triangles, there's a 0 vertex, a 1 vertex, and a 2 vertex. So let's think about what that means. Let's see if I can get it to track. Nope. Can you just push the... Thank you. It was tracking so well for so long. No, just touch the iPad. Just push the iPad. Okay, thanks. Okay, so now, not to scale, here's a 0, 1, 2 triangle, say. What this means is that when we apply our function f, this is the first coordinate that is different, is 0. This is 2, this is 1. What happens as the triangle gets smaller and smaller and smaller? It's converging to a point. And we're assuming our function is continuous. So this is the contradiction. And then this becomes the question of how rigorous do we want to make this step?
Where did this smaller triangle come from?
Well, I'm saying we have a chain of triangles and small triangles and small triangles and small triangles. And so we have a sequence of points 0, 1, and 2 that are converging. And if we look along this path, it's converging to some point. So look at it this way. We have some special point here, and we have, let's call it the 0 path. And along this path, the first index that's different. Then we'll also have a 1 path, which is going to be very close to this, but maybe it's coming in like this is the 1 path. And then we'll also have the 2 path, which is also going to be close. I'm just drawing it like this just to make it a little bit easy to see. And so as I approach this point, if I consider myself approaching it along the 0 path, the first coordinate is going to be different. It's going to be different, it's going to be different, it's going to be different. But in the limit, does it still have to be different? What could it be if it's not different? I'm sorry? Well, I'm saying if I look along these points, if I look at P versus f of P, along this path, f of P has a smaller t0 component. And it has a smaller t0 component for every point along this. When we get to here, I claim they no longer have to be smaller. They could instead be, they could be the same. Could it be greater? No, because along this path, f of p is always less than or equal to. So in the limit, since it's continuous, you can go from a strictly less than to a less than or equal to. But you can't go from a less than to a greater than. So if I look at what's going on in the limit, so let's give this special point a name, call it p star. And so we have p and p star. And we'll call this, TP0, TP1, TP2. And we'll have TP star 0, TP star 1, TP star 2. And we know that TP0 is greater than or equal to TP star 0. Right? Because as long as we're moving along this path, every time we move along this path, when we apply f, the new point is going to be strictly less than. So in the limit, it's less than or equal to. We know this is also less than or equal to. We know this is also less than or equal to. So each component of p star is less than or equal to. All we have to do is get rid of the less thans. How do we get rid of the less thans? I'm sorry? Say that again? So we know TP0 is greater than or equal to TP star 0. The sum is 1, and this sum is 1. So if there was a strict inequality, you would have 1 is strictly less than 1. So as sum to 1 must be equal. And that's Brouwer's fixed point theorem. So I will post later tonight some of the incredible consequences. This is a major theorem. This is not just, well, I had to do something because I was coming to Swarthmore, and let's just throw something on the board. This is major mathematics. This is the mathematics behind Nash equilibrium. And it all comes down, at least this proof, there's other proofs of the Brouwer fixed point theorem. It all comes down to the smallest odd number is positive. And then what I like is you get to see where these results from real analysis come into play. Why do we care about things like Bolzano-Weierstrass? Why do we care about these continuous arguments? Here's an application. And then you want to ask, well, where will I actually get a setting where I can apply something like the Brouwer fixed point theorem? So if you're interested in economics, I will post some stuff where you can read about Nash equilibrium and how he can use this to prove that there is an optimal strategy in certain game situations. One of my favorite classes to teach at Williams is operations research. I lectured on this last semester. It's important to note that just because an optimal strategy exists does not mean that you have an efficient way of finding it. And a lot of times, it does very little good to come to the boss and say, good news, I've proved that there's something our company can do that will get us out of this hole we're in and we'll make money. What should we do? Well, I don't know. That's not my department. That's the engineers, the applied mathematicians. I proved that you can give them the job now. So, in practice, is this a useful theorem? It tells you that at least your search is not in vain, that there is something to look for. That's it. If you're going to spend your time searching for something, it's good to know that it exists. But is it constructive? Does this give you a way to find things?
Well, following this algorithm, we already have this series of
a whole lot of 0, 1, 2 triangles.
Right, but the problem is where the 0, 1, 2 triangle is can keep hopping around as we do the subdivisions. What we would love to do is the following. Here is a 0, 1, 2 triangle. Let's subdivide this 0, 1, 2 triangle. We can't subdivide the 0, 1, 2 triangle because we don't know that all the labels down here have to be 0, 1. That's what's so annoying about this, is you have to go back to the original triangle and subdivide the original triangle. And then you'll get points that are closer and closer and closer, but it may not be a fixed point. So in terms of practicality, this is bad. Now, a contraction map, do we still have like do we still have 2 minutes? I think somebody had something at 6. Or do you have time to just quickly do a contraction map? And then after this, we'll run to the airport. Because I'm not going to give American.
That might be quicker than driving.
See, I'm a Boston driver, so worst case scenario, just to get me behind the wheel. Boston driver means I drive very safely even when there's a lot of traffic. So contraction map. So f of x minus f of y is strictly less than or equal to c x minus y for some c strictly less than 1. So it's very important that the c is independent of x and y, and it's strictly less than 1. It's not enough to say that it's strictly less than 1. So what this means is if you take 2 points and you apply your map, you get closer. And it turns out every contraction map has a fixed point. And there's a really nice way to find a fixed point of the map f. Start with some point x naught. x1 is f of x naught. x2 is f of x1. x3 is f of x2. And just keep iterating. So no matter what point you start with, if you just keep iterating, you will get to the fixed point. And what's lurking is a geometric series. And as you keep applying this, so if I try to look at, say, f of x4 minus f of x3. This is going to be less than or equal to c f of x. So x4. No, okay. It's c times x4 minus x3. But x4 is f of x3. So this is less than or equal to c f of x3 minus f of x2. Well, that's going to be less than or equal to c times c x3 minus x2. So that'll be less than or equal to c squared x3 minus x2. And then you can keep going down, going down, going down. So if you've done real analysis, if you know what a Cauchy sequence is, you would look at f of xm minus f of xn, and you would get a high power of c, and you would show that it's a Cauchy sequence. And so this is why contraction maps are very nice, because not only do you have the existence of a fixed point, but you have a constructive way of finding the fixed points. And that's far more useful than just knowing that the fixed point exists. Okay, any questions on contraction maps, or you borrow fixed point theorem, Sperner's lemma? So a lot of great mathematics here, and to me, as I said, this is one of the reasons why I love teaching class like problem solving. It's trying to come up with what are the big ideas that you can then use to attack a variety of problems. One of the most important problems in mathematics is counting. Is your set empty or not? So I will end with a really nice joke that my advisor, Henrik Ivanets, told me. I'm not sure if it's due to him or someone else. Do you know the Riemann hypothesis? So the Riemann zeta function is one of the most important functions in all mathematics. The Riemann hypothesis states that all of the zeros, the non-trivial zeros of the Riemann zeta function, have real part of half. And what we have in number theory is we actually have bounds towards the Riemann hypothesis. And so here's 0, here's 1, here's the midpoint of the critical strip. We believe all the non-trivial zeros lie over here. Here's the line 1. We have these zero-free regions where we know there's no zero in a region like this, and the width of this is like 1 over log to a power of t, where t is how high up you are. But there are some results, if you look at boxes, and you say, how many zeros have real part greater than sigma up to a certain height? We have some bounds for how many zeros could be in this set. And not surprisingly, the closer sigma is to 1, the better the bound is. The closer sigma is to 1/2, the worse it is. And what my advisor said is, these theorems are trying to get better and better upper bounds on the cardinality of the empty set. I can prove the empty set has at most this many elements. If the Riemann hypothesis is true, the number of zeros with real part greater than sigma is 0, as long as sigma is greater than a half. We can't prove that, but what we can do is we can prove bounds on how many elements can be in that set. The Riemann hypothesis all comes down to, is this set empty or not? It's one of the hardest problems to determine, is there an element in the set? And the idea of Sperner's lemma, this idea of oddness. We use even oddness to actually determine sign changes in functions. If the function's positive here and negative here, if it goes through a sign change, it must have a 0 if it's continuous. This is actually how we find zeros of the Riemann zeta function. There's a function related to it which is real on the critical line, and we just count sign changes. So these are not just trivial ideas. These are ideas behind a lot of good mathematics. All right. This is at the point where I think even American Airlines might be able to. So I will turn it off here.